Okay, so we're going to continue with our geometric series and sequences here with just some application problems. First one is just repeating decimals. I could rewrite this as 1 plus 0.35 plus 0.0035 plus 0.00035, and that would continue. Okay, so what we're looking for here is a geometric series where we're multiplying by 0.01 each time. So our sum here is going to be 1 plus the sum. So that's going to get us 1 plus the first term here, which is 0.35, all over 1 minus 0.01. So that's going to get us 1 plus 0.35 over 0.99. And if we were trying to add these guys together, I could multiply this by 100 over 100 over here. We don't want decimals here. So it's going to get us 1 plus 35 over 99, changing to common denominators. So it's going to be 134 over 99. Now I can show you a little trick here. If it's 2 repeating digits, it's going to be over 99. If it's 1 repeating digit, it's just going to be over 9. So this is our fraction here. You could also rewrite this as 1 over 35 over 99. Over here, doing it the real way, this could be written as 14 plus 0.2 plus 0.02 plus 0.002. Continuing on, I can see here that my common ratio is 0.1. So basically what this is going to be is 14 plus the sum. So this is going to be 14 plus the first term, that's a plus over there, over 1 minus 0.1. We get 14 plus 0.2 over 0.9, multiplying by 10 over 10. We get 14 and 2/9. We could go ahead and multiply out here. 19 times 14 plus 2 is going to get us a total of 128 over 9. And again, since there's only one repeating number, it only goes over 19 here. We could show, this is just kind of a fun little fact here, or a proof, trying to show that 0.9 repeating is the same thing, oopsie, we do not want that, is the same thing as 1. So what I'm looking at here, I want to prove that 0.999 is equal to 1. So this is going to be 0.9 plus 0.09 plus 0.009 plus continuing on is equal to 1. This becomes our a sub 1 over here. So we want to show that our sum here is going to be equal to 1. Our a sub 1 is 0.9 and our r value is 0.1. So what over here, this is what we're looking to prove. So this is going to be 0.9 over 1 minus 0.1 is equal to 1. We do get 0.9 over 0.9, and we now proven that those are the same numbers. Okay, we're going to be looking at a bouncing ball. So a ball is dropped from a height of 30 feet. Each time it strikes the ground, it bounces up 80% of its previous height. This is a 4-part question here. So we start at a total height of 30 feet. The ball goes down for the first time it hits the ground. It goes up 80%, and now we're at 24. It goes down for the second time. It goes up 80%, and now we're at 19.2. It goes down for a third time, it comes up 80%, and now we're at 15.36. I want to know what height will the ball bounce up to after it strikes the ground for the third time. So our answer is this answer here of 15.36. Then I'm asking, okay, well then how high will it bounce after it strikes the ground for the nth time? Now we're looking for a formula. I know my a sub 1, this is a sub 0, that's where it initially started. So our a sub 1 is actually the first time it comes up, which is 24. And our R value, again, is 80% of 0.8. So a sub n is going to be 24 times 0.8 to the n minus 1. So there's our formula for that. And how many times does it need to bounce before it bounces less than 6 inches? Our original formula is in terms of feet, so 6 inches is equivalent to 0.5 feet. I'm going to use this formula over here. I want to know when are we going to get to 0.5. So 0.5 is equal to 24 times 0.8 to the n minus 1. Dividing through by 24, I get myself 1 over 48. You can use a decimal here, that would be okay. 0.8 to the n minus 1. Now we just learned in our last unit, in order to get up into that exponent there, we're going to need to take the log of both sides. So I'm going to take the log of 1 over 48. It's going to equal the log of 0.8 to the n minus 1. The reason I want to go ahead and do this is now I can move this piece here to the front. Alright, so now we're looking at the log of 1 over 48 is equal to n minus 1 times the log of 0.8. I'm going to go ahead and divide each side by the log of 0.8. We do get a numeric value over here. We do get 17.35 is equal to n minus 1. Adding that 1 over, so it's going to be 18 times. It'll take 18 times for it to get to be about 18.35 exactly, to be that n value that we're looking for. Okay, and the last thing I want to know is what is the total distance traveled? So now we're looking at a sum. So what we're looking for here is the total distance traveled. Now this time we actually do need to include 30. So we're looking at a sub n of just going down. Just the down bounces at first. It's going to be equal to 30 times 0.8 to the n minus 1. So over here, we're looking for the sum of this here. The sum of the down bounces is, oh boy, I don't know what's happening there. Let's try that again. All right, sorry about that. So a sub 1 of just the down bounces is equal to 30. It started at 30 feet, 0.8 to the n minus 1. The sum of these numbers here is going to be the first term over 1 minus 0.8. That's going to get us a total of 150 feet. Then we want to look at our a sub for the bounces going up. Up, we're heading at 24 times 0.8 to the n minus 1. We want this sum here, so it's going to be 24 times 1 minus 0.8, getting us a total of 120 feet. We will need to add these two numbers together, and we get ourselves 270 feet. Okay, and the last piece here, our last problem, is depreciating value. We have a new piece of equipment that costs the company $15,000 new. Each year, for tax purposes, the company depreciates the value by 15%. What value should the company give the equipment after 5 years? So when it is new, that piece of equipment is worth $15,000. After year 1, it is only worth 0.85% of that. So it's a sub 1 times 0.85, and that's going to give us 12,750. So there's our a sub 1. At year 2, it's going to be 0.85% of that number here, and that's going to get us 10,837.5. So over here, for our formula, what we're looking for is a sub n is equal to a sub 1, which is the first one. This is really A sub 0 what it is at new. First year here, it is worth $12,750. I know our R value is 0.85 to the n minus 1, and I want to know what it's going to be after year 5. 0.85 to the 5 minus 1, and when you get that in a calculator, this particular piece of equipment will be worth $6,655.88. Okay, and that is going to finish up our applications of the geometric sequences.